and this thing called the K sub m. Hello, welcome back to Educator.com. Welcome back to Biochemistry. So today we're going to continue our discussion using this thing called the Michaelis-Menten equation that we introduced in the last lesson. So we introduced this idea of the velocity max and this thing called the K sub m, the Michaelis-Menten constant. Very, very important. So in this lesson, what I'm going to do is give you an alternate version of that, where instead of estimating Vmax and estimating the Km like we did in the previous lesson, we're going to develop an actual analytical method where we actually come up with some really, really exact values for this. So let's just jump right on in. It's actually quite simple. Okay, so let's go ahead and start off with our Michaelis-Menten equation again. So that's fine. I guess I can stick with black. It's not a problem. So we said that the rate of the reaction, the speed at which it's going, is going to equal some maximum velocity times the substrate concentration over this Michaelis-Menten constant plus the substrate concentration. So this is our initial equation. Well, let's do something to this equation. Let's actually reciprocate the left side and the right side. Let's just flip it and then manipulate it algebraically to see what we might get. When you do that, excuse me, you end up with the following. You end up with 1 over V0 equals Km plus S over Vmax excuse me, times S. Now we have everything under one denominator. There's only a single term in the denominator. So let's separate those out and see what happens. You end up with 1 over V0 equals Km over Vmax times S plus S over Vmax times S. These S's cancel. Let me rearrange this. This term right here. This term right here is the same as Km over Vmax times 1 over S. So I end up with 1 over V0 equals Km over Vmax times, let me put that in parentheses, times 1 over S plus 1 over Vmax. This equation, it's called the double reciprocal equation. Double reciprocal because I took the reciprocal of the left and the right. Also called the Lineweaver-Burk equation. That's what's important. Notice the form of this. This is y equals mx plus b. And this is the equation for a line. Y is 1 over v0. M, the slope, is Km over Vmax. 1 over S is the independent variable. And 1 over Vmax, that's the y-intercept. So here's what you do. When you're given rate concentration data, like the previous lesson, what you do is you create two new columns. You take the reciprocal of the substrate concentrations that you used. That's going to be another column. Those are going to be your x-axis. And you take the reciprocal of the velocity values that you got, and that's going to be your other column. That's going to be your y-axis. You're going to plot this out. When you plot this out, here's what you're going to get. So, on this axis, we have our 1 over S. On this axis, we have 1 over V0. When you plot this out, the 1 over V0 versus the 1 over S, you're going to end up with a line. Some straight line like that. Here's what's great. The y-intercept, well, that's equal to, let me actually rewrite the equation here again so we see it. So we had 1 over V0 equals Km over Vmax times 1 over S plus 1 over Vmax. Well, this y-intercept, because it's It's 1 over V0. So it's not V0 versus S anymore. It's 1 over V0 versus 1 over S. You get a straight line. Where it hits the y-axis, that's equal to 1 over Vmax. So you literally read this number, you set it equal to Vmax, you switch the two, you solve for Vmax. It's an analytical way of finding Vmax. Where it hits the x-axis here, this is equal to minus 1 over Km. And the slope of this equation is equal to Km over Vmax. And that's the slope. That's the y-intercept. So we have an analytical method based on rate concentration data. Create two new columns of data, 1 over concentration, 1 over velocity, graph that, take the two intercepts, solve for Vmax, and solve for Km. So now we have a precise way. We don't have to anymore estimate where the Vmax is going to be and then take half of that and then find the Km. Now we have a nice analytical procedure for finding Vmax and Km. That's it. That's all that's happening here. So, again, when given data that includes substrate concentration and various initial rates. In other words, when you're given substrate initial rate data, when you're given data that includes substrate concentrations and various initial rates, we form new data. And the new data we form is 1 over those substrate concentrations and 1 over the initial rates, and plot this. From the plot, we calculate Vmax and Km. Pretty standard when dealing with a new enzyme. You've purified a new enzyme. One of the first things you do is you run these, initial rate experiments, and you find its Km and you find its maximum velocity under a certain set of conditions and for that particular substrate. That's it. So that's it. It's literally that simple.